Here we are again. We're in section 1.2. In section 1.2, we're working on the definition of divides and divisibility. Definition. Let A and B be integers with B not equal to 0. We say that B divides A, or we can also say that B is a divisor of A, or that B is a factor of A, if there exists an integer C such that A is equal to B times C. So when B divides A is bigger. And when A is bigger, we're going to have A equals, and that means there exists an integer C such that A is equal to B times C. Now, when we're rounding up proofs, this is a writing intensive class, so we use a minimum of symbols. And so the little slash for divides we will not use. You'll see that in Dr. Hungerford's book, but when he comes up with his actual proof, he writes the word divides out. So we're going to use a lot of words on this thing because it's a writing intensive class, but you're not allowed to use the symbol divides with this particular material. So with this being said, we have some examples here. And so let me write up my examples. I'll slide this up a little bit so you guys can see this. All right. We know that 3 divides 27. Now, why does 3 divide 27? That will actually imply, and I'll use some symbols here, but when you're writing a proof, you don't get to use that. 3 divides 27 because there exists an integer 9 such that 27 is equal to 3 times 9. You can write an equation. But 8 does not divide 27 because I can't write an equation. To actually get 8, 27 would be equal to what? 8 times 3, which is 24, plus 4. That plus 4, you don't have that nice little A equals B times C looking type of an equation here. So we'll do some side notes here. If A and negative A, A and negative A and negative A have the same divisors. So in other words, it doesn't matter if you're actually working with positive numbers or negative numbers with these integers, they're going to have the same divisors. Okay? Remarks. Every divisor of a non-zero integer is less than or equal to itself. So if you're talking about the divisors of 27, any kind of divisor of 27 has got to be less than or equal to 27. Again, assuming that the factor you're looking for is a positive number there. And number 2, a non-zero entry only has a finite number of divisors. You know, if you've got an integer, you're only going to have a finite number of divisors with this stuff. So, an example here. What are the divisors of 24? So, we'll write the divisors here. And the divisors are, let's see here, now 1 divides 24, of course. So it's 1, 2, 3, 4, 6 divides 24, 8, 12, and 24 itself. However, remember, a divisor can be either positive or negative. So every one of these guys, you got plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 8, plus or minus 12, and plus or minus 24. A grand total of 16 divisors. 1, 2, 3, 4, 5, 6, 7, 8, plus or minus times 2, 16 divisors 24 has. Okay? Now, the next definition is the definition of GCD, the greatest common divisor. So, again, classic abstract modern algebra, you got to let letters represent numbers. So, definition, let A and B be integers, not both 0. Then the greatest common divisor, GCD of A and B, is the largest integer D that divides both A and B. So, a lot of people kind of mess this up here, but the greatest common divisors is the biggest small number that divides into both these guys. Because if you're going to be a divisor, you're going to be smaller than A and B. But it's the biggest small number that divides both A and B. So in other words, if D is the GCD of A and B, then that means provided that D divides A and D divides B, and if C divides A and C divides B, then C is going to be less than or equal to D. So any other divisor will be smaller. D will be the greatest of the divisors. So, with that, now let's talk about your book for a second. In your book, Dr. Hungerford's book, we typically write the word GCD. So D is going to be the GCD of A and B. We would write it as, and this will be us here, we would write it D equals the GCD of A and B. From old school of GCD being the greatest common divisor. However, the book, they're going to write it D equals parentheses AB. Now, somewhere in the directions they'll talk about GCDs, and it's supposed to be implied that this is the GCD. But this bothers me because this looks more like an ordered pair or some kind of a vector or something like that. And that's not what it's supposed to be. It's the GCD of this guy. So when I write this stuff up for you guys, I'll keep putting the word GCD in there. However, when you do read this thing out of the book, you're going to actually not see Dr. Hungerford write GCD in front of the A and the B. So an example here would be this. What is the GCD of 12 and 30? In other words, when I ask for that, what is the biggest divisor of 12 and 30? Now, most of us can look at this stuff and go, oh, clearly, I can look at divisors and think about them in my head and go, all right, 12 can't go into 30, so it's not 12 itself. Factor of 12 would be something like maybe 6. 6 goes into 12 and 30. Yep, the GCD is 6. And we do a mental game on this thing, and we get the correct answer. Okay? But when the numbers get a little bit bigger, this is going to be a pain. Now, yes, you're right. I know there's a button on the old calculator that we can use for GCDs. It's under the math thing, and that's great. But we want you to be able to figure these things out mathematically and through an algorithm. So we're going to come back to this idea of how to find GCDs when they're really big. But here's another example here. What is the GCD of 24 and 36? So get a little bit bigger here, but don't think about it. What's the biggest divisor of both 24 and 36? And again, you should be able to look at this thing and go, oh, clearly it's going to be 12. Okay? But when we get into a little bit bigger ones, the GCD of 180 and 315, now it begins to worry us about finding the GCDs and stuff. So, if you remember way back when we were talking about divisors and prime numbers, which we'll get into later, of integers, the trick that we were taught, I don't know, 5th grade or something like that, about GCDs was prime factorization. So if you look at this thing, let's break down 180. Now 180 is, we'll do it easy, 18 times 10. Well, we can break that up. 18 is 9 times 2. 10 is 2 times 5. 9 is 3 times 3. And then bring down your times 2 times 2 times 5. And this is what we call the prime factorization. 180 is 3 times 3 times 2 times 2 times 5. Now, if I go in there and figure out what 315 is, well, let's see here. 5 clearly goes into this thing, so I can divide 315 by 5. 3 doesn't go into 5 doesn't go into 3, but it goes into 30. 6 times 5 is 30. Subtract, bring down to 1, 5. 5 goes in 15 3 times. That'll be 15 remainder 0. So 315 is 5 times 63. Now, we want to sit there and factor out what 63 is, because 5 is prime, so leave that 5 right there. Now 63. What times what is 63? That would be 7 times 9 is 63. Factors we know. So that would be 5 times 7. 7 is prime, but 9 can be broken up into 3 times 3. And so my prime factorization for 315 is 5 times 7 times 3 times 3. Now, the question is, what's the GCD? The GCD is the greatest common divisor. So what factors do they have in common? They have a 3 in common, they got another 3 in common, and they got a 5 in common. That's it. So the GCD is actually going to be what's in common on the prime factorization. 3 times a 3 times a 5. And 3 times 3 is 9 times 5 is 45. So the GCD is 45. And this is typically how we were taught way back when in the 5th grade, when we were talking about prime numbers and really getting into the multiplication and the idea of prime factorization and stuff when the numbers are big. Now, a lot of them we can look at them and just tell what the biggest factor is, but sometimes when they get really big, we do this. The problem is this is not efficient. This is how we were taught way back when, but there are more efficient ways, especially this day of using computers. So there's better algorithms to actually find GCDs, and we're going to be looking at that a little bit later. Now, what's important about these GCDs is this. Theorem 1.2. This is a big theorem out of our textbook. So, things worth memorizing here. Theorem 1.2 says this. Let A and B be integers, not both 0, and let D equal the GCD of A and B. Then there exist, not necessarily unique, integers U and V, such that D equals A times U plus B times V. Okay? And D is the smallest positive integer that can be written in the form of D equals AU plus BV. Because in terms of that greatest common divisor, to be greatest, remember divisors can be positive or negative, but to be the greatest, since positives are bigger than negatives, a GCD is always going to be a positive integer. So this positive integer D is equal to A times some integer U plus B times some integer V. And D is going to be biggest factor of both A and B that can be written like this. Okay? So, understand what this theorem is telling you. If I give you D as a GCD of somebody, A and B, automatically by Theorem 1.2 there exist integers U and V such that you can write an equation. But, remember this, it's a one-way implication. If you got the GCD, you can write the equation. Just because you can write an equation for a couple of integers U and V does not imply that what it's equal to is going to be the GCD of A and B. So it doesn't go the other way. If you got the GCD, you can write an equation. If you can write an equation, who cares? That may or may not be the GCD. I can multiply everything by 2 and make this thing twice as big, and that doesn't make 2D the GCD or whatever. So if you got the GCD, there automatically exist integers U and V such that D equals AU plus BV. But if you just got an equation, that will not imply that you actually have the GCD. So let's go back and take a look at some examples that we did. So you remember that what was the GCD of 12 and 30? That last example we did. Well, we did that one in our heads and we got 6. Well, according to this theorem 1.2, there's going to exist some integers U and V, not necessarily unique, such that I can write 12U plus 30V will be equal to the GCD, which is 6. Now the question is, what's U and V? Well, there's lots of examples here, but what if I do this? 12 times, if I let U equal to 3 plus 30 and I let V be negative 1, that would be equal to 6. 12 times 3 is 36. 30 times negative 1 is negative 30. 36 minus 30, yeah, it's 6. That works. But also notice this. I could have done this. 12 times negative 2 plus 30 times a positive 1. Let's see what we get there. 12 times negative 2 is negative 24, plus 30 times 1, 30, 30 pretty much minus 24 is 6. You see, here's one set of u and v, here's another set of u and v. They're not necessarily unique, but you're going to get 6 to be the equation, and 6 is going to be the smallest integer that you can be able to write in this terms of equation, because the GCD of 30 and 6, actually 12 and 30 is 6, so you can be able to write these equations, but the u and v are not necessarily unique. So let's do another one. Remember, we also said that the GCD of 24 and 36 was 12. Let's just write that down again. The GCD of 24 and 36 was equal to 12. So how can I come up with those type of equations? Well, let's see here. 24 times some u plus 36 times some v should be equal to 12. Now, finding u and v usually is pretty easy, but not always. Depends on what the numbers are. So if I did this, 24 times, well, pretty much the difference between these two. So if I make u negative 1 and 36 times v positive 1, yep, that's pretty much 12, and you win the game right there. So that one was actually pretty easy. But again, with that not necessarily unique, I can sit there and take 24 times 2 plus 36 times negative 1, and that also gives me 12. Different set of u and v. U and v are not necessarily unique. Okay? And just for good practice, remember we also played around with the GCD of 180 and 315, and that was equal to 45. So 180 times what plus 315 times what equals 45. And so if you play around with this thing, you start, well, you'll notice very quickly that one of these number integers is going to be positive, one's going to be negative, so because this is a smaller number than typically what you start out with. So if I remember on this one, I think if I do 180 times 2, that's 360, minus 350, if I make that negative 1, that also gives me 45. And there's more u's and v's than just 2 and negative 1 that'll do it for me, but hopefully you can get these guys rather quickly. But when you can't, there's another algorithm that we're going to be talking to you guys about and stuff. So if we come over here, now we're going to talk about Corollary 1.3. Now before I talk about Corollary 1.3, all these wonderful math terms ought to come back and start honing you about this particular stuff. The idea of theorem, corollary, and lemma. So when we look at these guys, we want to figure out exactly what's going on. And so what's the difference between a theorem, corollary, and a lemma? Now, this is classic math and math proofs. Remember, the whole idea behind algebra is the idea of being able to prove stuff. So here we go. Now, here's kind of a unwritten rule about how things go, and there's a little bit written rule here. But when you're writing your dissertation, that's how you get your PhD in mathematics. You've got to come up with a theorem that nobody else has ever come up with. When you've got something that you prove it, and you think this thing is rather big, we call it a theorem. So a theorem is really a big idea, again, that has been proven. That's what a theorem is. It's been proven. Now, a lemma is, it's a big idea, but I really don't do much with it, so it's not that big of an idea. Because here's the real deal. When you start writing your dissertation, coming up with your PhD, you've got to come up with these new theorems. Usually when you create one, a couple of more typically fall out if you start playing around with this stuff good enough. So, but when you come up with an idea and you prove it, and it's nice, but it's not a cornerstone that other theorems typically fall off of. We call this a lemma. A lemma is, for lack of a better term, a small theorem. Small idea. Now, the next one is the idea of corollary. Now, a corollary, I'll put him in the middle. corollary is a theorem itself, but is a theorem that follows another big theorem. So, when we're sitting there talking about these guys, I got this big theorem that came up with it. And immediately after that, a couple other theorems using the same information tend to pop up. Same ideas, same setup. We would call these corollaries. And you have theorem and corollary, so you know when you have a corollary, it follows from a big theorem. So these are all kind of related and connected. If you're working along and you come across an idea and you prove it, but it's not really connected to anybody, we'll call him a lemma. Lemmas typically don't have corollaries that follow them. And it's kind of an unwritten rule of how to know the difference between all three of them. The fact is, all three of them are theorems in themselves. But that word theorem to corollary means a corollary, this theorem is actually connected to a bigger theorem. And a lemma, this guy kind of stands on his own, and he's just a thought. I mean, maybe a big idea, a small idea, but it doesn't have a bunch of stuff following behind it and stuff. So, this is corollary 1.3. Corollary 1.3 follows from big theorem 1.2 there. Corollary 1.3. Let A and B be integers, not both 0. And let D be a positive integer. Then D is the greatest common divisor, the GCD. D equals the GCD of A and B, and that's traditionally how I would write it. If and only if D satisfies these conditions. D divides A and D divides B. And number 2, if C divides A and C divides B, then C will actually divide D. Now, a couple of things you should realize here when looking at this. Number 1, I want to talk about this idea of if and only if. Okay? So, if and only if. When you see that, its typical mathematical symbol for that is a two-way implication. Now remember, we're not going to use a bunch of symbols, especially in the first part of the class. As we move on, start using more symbols within our theorems and proofs and stuff like that. But if and only if is actually meaning of double implication here, which means this. In this theorem, if D is the GCD of AB, you get these conditions. But it also goes the other way. If you got these conditions, that will force D to be the GCD. So you start with one and it proves the other, and if you add the other, it starts with the first guy. So you can basically prove both ways. So this is a two-way proof type thing here. Now, what you should realize about Corollary 1.3, honestly, is that it looks awfully familiar with the definition. So I'm bringing back an old page up here, and so I'm going to see if I can kind of put these two guys together and take a look at them. Okay? Now, if you look at them, Corollary 1.3 and definition of GCD, they start out the same way. Let A and B be integers, not both 0. Then the greatest common divisor, GCD of AB, is D, provided we have this argument. So this is your forward way, and it comes directly off the definition. And so here it comes. What does the definition say? D divides A and D divides B. Yep, exactly the same. But the definition is slightly different. If C divides A and C divides B, then C is less than or equal to D. This corollary is a little bit stronger. Not only is C less than or equal to D, C will actually divide D. Okay? So this is the definition. So if you have this, you've got the GCD. If you got the GCD, you get this for free. So in the definition, you kind of got this two-way street going on. This is pretty much the same thing except for one little thing. It's stronger. Not only is C less than or equal to D, it actually divides D. So again, these are the big ideas with this GCD. You can go both ways, and this C divides D is going to be quite helpful in certain proofs and things like that as we get into this stuff. But right now, we're just getting into some of the definitions, and the like. Now, I want to do a proof that is very straightforward and stuff, but this is what the class is really all about, is proofs. So I've given you all these theorems and definitions, and you honestly really need to memorize these guys. And I will have a little cheat sheet on test where you can have a little quick reference of the major theorems that you typically reference within a proof and stuff. But I want to actually do a problem that you were actually see an actual direct proof. Now, when it comes to proofs, you should be familiar with proof by induction and proof by contradiction, or things like that in other math classes. But if you haven't, no worries. But in this class, our focus on is direct proofs. I'll occasionally do an indirect proof with you guys, basically a proof by contradiction. But you should be familiar with our proof by induction. Proof by induction is one of these proofs that you use a formula for, that you go through steps. And the proof by mathematical induction is you basically have a formula. You show it works for the base case, like n equals 1. You assume it works for n, and then you work the next case. You prove it'll work for n plus 1 by manipulating the equation or whatever and showing that when it works for n, the pattern will also show it for n plus 1. That's called proof by mathematical induction. You see that in the discrete math classes and like. But the ones we're going to do is direct proof. So I'm going to write this guy up for you guys the way it literally should be written up in terms of this. And again, very little on the symbolism, but equations are okay. It's all about equations and manipulating equations. Remember that. So here's my proof. So given this, theorem 1.4, and we know it must be true because we call it a theorem. So here it is. Let's prove it. If A divides B times C, and the GCD of A and B equals 1, by the way, that's called A and B are relatively prime when they have a GC of 1. I'll define that later. Then A divides C. Then is what I want to show. A divides C. Now, you're going to, right at the beginning of this class, you're going to do a lot of proofs about showing somebody divides something else. And remember the definition. To show that, quote, A divides C. Remember, this is algebra. It's all about equations. I want to write an equation with C equals A times, and I got to show you that it's going to be some integer. Okay? I'm trying to get equations out of this guy. The trick to this course is integers. Coming up with equations. And the first part of this class, we're dealing with integers. So coming from integers to equations is actually not that bad. So you first start out a direct proof with the givens. So I'll still use that word, given. Given that A, if means given. Given that A divides B times C. Let's first start with that. That's my first given. We're also given the GCD of A and B is 1. We'll talk about that in a second. But here we go. Given that A divides B times C, then by definition of divides, I can come up with an equation, but I got to declare a variable before I can use it. By definition of divides, there exists an integer, and here you go, classic algebra. I got to come up with an integer, and we got to let a letter represent an integer. So pick any letter you want. I like x. There exists an integer x such that now we get to write an equation. A divides BC. Who's bigger, A or BC? If A divides BC, BC is bigger. So BC would be equal to A times that integer x. And I got an equation out of it. Okay? Also given, so stop for a second, we've got an equation, we'll go to the next part. Also given that the GCD of A and B is equal to 1. Well, when you got GCDs, that theorem 1.2 allows us to go from GCDs to equations. That's why that theorem 1.2 is so important. So, also given that GCD of AB equals 1, then by Theorem 1.2. You got to tell me why and what reasoning here. Definition of divisors was in this part. Now it's Theorem 1.2. There exists integers, and I'll use my favorite variables that I haven't used before. You can use any letters you want to. You just kind of make them up as you go along. But I'm going to use the famous letters from the theorem. Exist integers u and v such that AU plus BV equals the GCD, which is 1. And again, I got an equation. Now, here comes the puzzle part of this thing. What do you want to show? I mean, I took the two givens and I wrote an equation. I took the other given and by theorem, I wrote an equation. I want to show that A divides C, which means by definition divides. I want to show C equals. I don't have an equation with C equals, but I got to create one. Well, how do I create an equation with C equals? Well, I got BC equals AX. I could divide it by B, but you put integers, you don't want to divide. Gives you fractions, that's rational numbers, that's not proofs. We gotta have a classic equation with nothing but integers. But I have this guy here. AU plus BV equals 1. I can turn 1 into any integer just by multiplying by the integer on both sides. And that's what I'm going to do. So as, notice a wonderful writing up of a proof. So as AU plus BV equals 1, then C times AU plus BV is equal to C times 1 by multiplying by C on both sides. State what you did in the proof. I took that equation, I multiplied by C on both sides. Thus is a great linking word. Let's work some algebra here. CAU plus CBV is equal to C times 1, and C times 1 is just C, by algebra. Alright, now we're in chapter 1.2. Later on, we're going to be very more specific about this. What I really did was I distributed the C on both terms there. And 1 times C, property of multiplying by 1 is C, but we'll just call that algebra for right now. Later on, I'll get more definitions. It's a very definition-heavy class here. Okay? So I got my equation. I got an equation equal to C. But if I want to show that A divides C, I want to be able to factor out an A, basically, and maybe multiply A times some integer by my definition. Well, I've got an A here, but I've got to put an A over here. So as C is equal to CAU plus CBV, and as, remember that other one, BC was equal to AX, then C is equal to CAU plus CBBC, same thing with integers. You have commutativity, it doesn't matter about order, but I can substitute BC for AX. So plus AX times V by, and you tell me what you did there, substitution. Now I've got my A's into my equation. Thus, C is equal to A times CU plus XV by, just to let you know what I did, factoring. Now, according to the definition of divides, if I want to show that A divides C, I've got to show C is equal to A times some integer. I believe this is my integer, but why would this guy be an integer? Well, since C, U, X, and V are integers, then C times U plus X times V is an integer. Remember, this is a writing intensive class, so get used to this. Writing a lot. Remember, the sums and products of integers is integers. That's why we like integers. The problem with integers is when you divide, but we're not dividing here. C times u, an integer times an integer is an integer. X times a v is an integer plus an integer. That guy is going to be an integer. Since the parts are an integer, the whole thing's an integer. Therefore, by definition of divides, and state what you want. A divides C. And when I'm done with the proof, I'll look at a little notation right there at the end just to let me know I proved it. Now, this is a direct proof. And this is what I'm looking for in terms of the proof class. And it's a pattern. And you got to get used to this pattern. Now, the first real math proof class you guys have probably ever played around with was in high school with geometry. And that idea of statement and reason. Statement, reason. You know, congruent parts, congruent triangles are congruent. That's why these triangles are congruent, whatever. You always have to use a statement and a reason. And I'm doing the exact same thing on a direct proof. On a direct proof, you have things like, okay, statement and reason. Well, given A divides B, C, then by definition divides, you've got to first claim him before you can use him. There exists an integer x such that BC equals AX. I have a statement and then my reasoning. So typically when you write up a proof, you talk about what you got, you state the reason for what something exists, and then you write and you really go after the equation, that statement reason aspect. Also given the GCD of B, A and B is equal to 1, then by Theorem 1.2, claim them before you use them. There exist integers u and b such that AU plus BV equals 1. Okay. So as AU plus BV equals 1, then C times AU plus C times C times AU plus BV equals C times 1 by multiplying by C on both sides. Thus CAU plus CBV equals C by algebra. And it's really distribution, and you can use fancy words if you want to. So as C equals CAU plus CBV, and as C is equal to AX, then C equals CAU plus AXV by substitution. And then I can factor out the A, thus C equals A times parentheses CU plus XV by factoring. But remember, I want to show that A divides C. So I want an equation with C equals, and I want to be able to factor out an A times an integer. But before I'm done, I've got to state why is this guy an integer? Well, since the part CU XV is an integer, then sums and products is an integer. CU plus XV is an integer. Therefore, by definition divides, A divides C. This is a classic write-up of a proof, and this is the kind of an example that you're going to be studying a lot of, especially right here in Chapter 1, in terms of getting this idea of statement reason. Now, wording is important, and what I'm after. I've had a lot of students sit there and go, given that A divides BC, then BC equals A times X for some integer X. Well, when you get really good at proofs, yeah, you can kind of trim some corners, and you'll see a lot of math professors at higher levels do that. But when you're introduced to modern algebra, order matters. That would have been wrong because you cannot use a variable before you can declare me to who he is. You can't say BC equals AX when you haven't told me who X is. You got to tell me who X is first, and then you write your equation. So, and notice, it's very much when we write equations, that's the symbols that are allowed. You want to write equations, not really symbols. And so with this stuff, it's all about me taking the equations and manipulating them to a point where, again, through a theorem or definition, I have proven what I'm after and stuff. So this is an excellent example and a great one to study. As we continue on with more stuff, we have here another theorem, and it's It's in your homework set. When you read your textbook, it's not a theorem per se as a classic theorem. It is actually one that actually is stated in your homework, but it's an important one, so I kind of pulled out of the homework and put it in our notes here. So when you're taking notes, copy this thing down. This is your first of many algorithms. This is called Euclidean Algorithm. It's a theorem, but again, it's in your homework set. It says this: let a and b be integers with a is greater than or equal to b. Then if b divides a, so a is bigger than b here, so if b divides a, then the GCD of a and b is equal to b. However, if b does not divide a, then apply the division algorithm repeatedly as follows. And remember, division algorithm, you can divide and get that remainder thing here. So, a would be equal to b times q naught plus r naught, and 0 is less or equal to r naught, which is less than b. We basically divide b into a, and you get a quotient plus a remainder, and your remainder is going to be less than your divisor. Okay? And then what you do is you shift. You take your divisor, it becomes the dividend. You take the remainder, and it becomes the quotient. And you keep doing it again. So you're going to take now the remainder and divide it into the quotient. And when you do that, the dividend, which was the divisor first, is equal to the remainder times a different quotient plus another remainder, where that remainder, R1, is going to be less than what you were dividing by R0. And again, we shift. And then you take the remainder, which was your remainder, which became your divisor, that becomes now the dividend. You take the remainder, and it becomes now the new divisor. So you're going to take R0 and divide by R1. You get another quotient plus another remainder, and you keep doing this procedure all the way down. Eventually, you're going to get a remainder of 0. So, continue the process until a remainder of 0. So, as we do this, we'll get RT minus 2 equals R of t minus 1 times QT plus RT, where 0 is less or equal to RT, which is less or equal to RT minus 1. And then we shift again, and so the divisor becomes the dividend, the remainder becomes the divisor, but then you're going to take RT minus 1 divided by RT is equal to, so RT minus 1 equals RT times QT plus 1 plus 0. Eventually, you're going to get a remainder of 0. And according to the Euclidean algorithm, here is the amazing thing about this. Here was the remainder of 0. The remainder before the remainder of 0 actually is the GCD of the A and B. And the GCD of A and B is actually equal to the RT. It's the remainder just before the remainder of 0 through the division algorithm as you implement it. And you look at this thing and you go, pretty impressive. What does it mean and stuff like that? Well, remember we talked about GCDs in 5th grade or whatever, you doing the prime factorization of integers and doing a comparison of those factors and figuring out what the GCD is and what's in common. That's not efficient. This is efficient. When you think of it from a computer science perspective, you can sit there and manipulate your program to divide and get your quotient plus your remainder, and you just keep doing the shift method, and eventually if you keep doing this pattern, you'll get a remainder of 0, and the remainder before the remainder of 0 as you analyze these equations ends up becoming the GCD every time. So, let me give you an example. So let me grab a nice little sheet of paper here. Here we go. Now, here's my question. What is the GCD of 324 and 148? What's it equal to? Well, yes, you can do your prime factorization. You can cheat and go grab a calculator, and that's awesome, and use the GCD button off that, but you're really not learning anything. Well, what we're going to do here is this. We're going to use long division and the Euclidean algorithm to show you what the answer is. All right. 148 does not divide into 324 evenly anyway. So here we go. I'm going to come over here and take my smaller number, which is 148, and divide it into 324. And it happens to go in there 2 times. 2 times 148, well, let's see here. 2 times 8 is 16, carry 1. 2 times 4 is 8, plus 1 is 9. 2 times 1 is 2. And when I subtract, borrow 1 from here, 14 minus 6 is 8. Borrow 1 here. 11 minus 9 is 2. So here comes my remainder. Here was my quotient. So this was my dividend and divisor. So from Euclidean algorithm, 324, division algorithm, excuse me, 324 is equal to 148 times 2 plus the remainder of 28. And again, this is from the division algorithm. The dividend is equal to the divisor times the quotient plus the remainder. So this is kind of my pattern here. All right, now remember that shift method. Shift 148 is equal to shift 28 times quotient plus the remainder. So I'm going to come over here and do long division again. 148 divided by the smaller number 28. Well, how many times does 28 go into 148? Well, 20 goes 148 about 5 times. Let's try it. 5 times 8 is 40. Put the 4 there. Put the 0 there and carry the 4. 5 times 2 is 10 plus 4 is 14. Subtract, I get 8. 28 doesn't go into 8, so here's my remainder again. Here's my quotient. So here we go. 128 is equal to 28 times the quotient, which is 5, plus the remainder, which is 8. And I shift again. 28 is equal to, now bring in your remainder, 8 times what plus what. So now your dividend is quotient from the last guy, 28, and your remainder becomes your divisor. So again, long division here, in case you didn't know it. 28 divided by 8. 8 goes into 28. Let's see here, I believe 3 times 8 is 24. Subtract remainder of 4. So again, your quotient is going to be 3, and your remainder is 4. So 28 is equal to 8 times 3 plus 4. Shift. 8 equals, remainder is 4 times what plus what. Now we got it down to 8 is equal to 4 times what? Well, it's 4 times 2 plus 0. And that's when I stop. I won the game. And here's the deal. From the Euclidean algorithm, the GCD of what we started with, 324 and 148, is going to be the remainder before the remainder of 0. So here is my GCD. The remainder is 4. Okay? Now, the other beautiful aspect of this thing is this, that remember Theorem 1.2. Theorem 1.2 said, there's also, again, I'll just quote it down here, Theorem 1.2 stated that there exist integers u and v such that 324 times u plus 148 times v is equal to that GCD, which is equal to 4. Now, what would u and v be? Well, here's the trick on this one. You take the Euclidean algorithm and you work it in reverse. Here is the GCD. It was 4. So we're going to solve for that guy. So I'm going to get 4 is equal to, I'm going to move this to the other side. That's equal to 28 minus 8 times 3. And I'm going to start there. And now I'm going to work backwards. I'm going to solve this guy for 8. Solving it for 8, that's 148 minus 28 times 5, moving this to the side, equals 8. And I'm going to substitute them in. And watch the algebra here. So what I get is 4 is equal to 28 minus, and replace that 8 with a parentheses, 148 minus 28 times 5, and that 3 still stays there, times 3. Now, you've got to clean it up. I'm going to distribute, and I'm going to distribute the negatives. Watch what happens. Distribute the 3 and distribute the negative. Distribute the negative and distribute the 3. This gives me 4 is equal to 28 minus 148 times 3. A minus makes it plus 28 times 5 times 3. Now I'm going to try to keep these numbers that were there originally. So watch what happens. 4 is equal to negative 148 times 3 plus, let's see here, I've got 28 here. It's officially 28 times 1 plus 28 times 5 times 3 is 15. So I've got 128, I got 15 28s, I have 16 28s. So 4 is equal to, and watch what I do, 148, I'm going to put the negative with the 3 here. Negative 3 because 148 was one of my numbers here, so I want to kind of focus on him not being negative. Plus 28 times 1 plus 15 is 16. So I'm kind of getting that U and V aspect of it. But wait, now I'm going to go up here and take this equation way at the top and solve for 28. And when I solve for 28, I get 28 equals, moving this to the other side, 324 minus 148 times 2. All I did was move this to the other side. And I'm going to take and substitute in for the 28 this equation, which has the A and the B that I'm actually after. So substituting it right in there, this would be 4 is equal to, down here you guys can see it, 148 times negative 3 plus 28 is substituted in for 324 minus 148 times 2, and that whole thing times 16. The 16 still stays there. I'm just substituting in for the 28. And now I'm going to distribute this, and the sign, well, it's a plus, but I'll distribute them anyway. So 4 is equal to 148 times negative 3 plus 324 times 16 minus, plus a negative is a minus, 148 times 2 times 16. Now, 2 times 16 is 32. So this is 4 equals 148 times negative 3 plus 324 times 16 plus, I'm going to make this a plus, that'll be 148 times, and put that negative with the number, negative 32. And combine like terms. I've got negative 3, 148's there. I've got negative 32, 148's there. Put them together. Negative 3 plus a negative 32 makes a negative 35. So 4 is equal to 148 times a negative 35 plus 324 times 16. So in terms of that, quote, U and V, U would be negative 35. Oh, wait a minute, that would actually be the V. Excuse me, put it in the right way. V, in terms of the way I wrote the equation, V is the number being multiplied by the 148, so V is negative 35. and the u would be equal to 16. Now remember, the 16 and negative 35 are not necessarily unique, but notice that if I try to go guess at it, I would have a real tough time to find that u and v, but I can use the division algorithm and algebra in reverse to be able to get that u and v. So practice this technique of manipulation and getting the integers and grouping together like terms so you can get it. The beauty of how this stuff ties together. Okay? So, the Euclidean algorithm. Well, with that, and here comes your first lemma. Lemma, again, meaning it's not a very big theorem in terms of ideas, but it's an idea here. All right, so if A, B, Q, and R are integers, and A is equal to B times Q plus R, then the GCD of A and B is going to be the same as the GCD of B and R. Now, I'm not going to actually go right proving this to you because the proof should be rather obvious. And it comes from this idea of the Euclidean algorithm and the idea of the remainder before the remainder of 0 is the GCD. Okay? So the GCD of A and B ends up being this RT. But when I shift, that also means the GCD of B and R0 is going to be RT. The GCD of R0 and R1 is going to be RT all the way down the line. And that's what's going on here. As you do the shift thing here, and I'll write that up with your Euclidean algorithm, once you do the shift, the B becomes the dividend, the R becomes the remainder, times the Q naught plus R naught aspect. The GCD of AB is going to be the same as the GCD of B and R. That's what this theorem is actually telling you. And we call it a lemma because it's not earth-shattering. It's a small theorem. That's the idea. Okay? So this is the end of section 1.2. And next time we'll move on into section 1.3, which is going to be dealing with primes and focusing more on the idea of a prime integer. So see you on that video.